We're going now to work the case and see in some details the parameters that will be needed for the link budget of the probe in different encounters in Jupiter and Neptune. But before, we are going to briefly comment on the instruments and experiments and the details of the mission that the Voyager carried away. This is just a simple scheme from the solar system. You can get all this data from the NASA website, and here you have the launch of the two probes. One went directly after Jupiter and Saturn went away. The other really took advantage of the gravity of them to really follow a path that brought it to Uranus and Neptune. This trajectory is only possible once every 175-76 years. So they really profited just to launch in that window of time to go by those four planets. Those four planets are the largest in the solar system. The inner four are really like the Earth, are rock, and they are solid and small. Those two fours are giants, and they are mainly made of gas. The first two, Jupiter and Saturn, are really made of hydrogen and helium, while Neptune and Uranus really have different gas and are really icy. So in the sense they are getting colder and colder as we move away. So those are the four planets that the probes visited. And here you have some data, some basic data. This is the launch. And 2 years later, they flew by Jupiter, then by Saturn, Uranus, and 10 years later after Jupiter, arrived to Neptune. Today, those are the distance, and maybe more than those numbers, the round trip, so to go from the spacecraft to the Sun and back, takes about 36 hours for the one, and for the Voyager 2, almost 30. Those are data at the end of 2014. And that's another image of another message that the probes carry on them. This is just a display of distance. You have here the planets. One astronomical unit is the mean distance from the Sun to the Earth. This is a log scale. So here you go to 10, Saturn, 100 times. And now they are around here. Voyager 1 is here, Voyager 2 is a little bit closer to the Sun. And they are said to be, one of them already in interstellar space, the other is still on the heliosphere. The closest star to us is Alpha Centauri, is here, it's about 4 light years. So it's still far, far away. So you can imagine how long it's going to take to get there. But still at this distance, both the spacecrafts are alive today, and they are sending about 160 bits per second of data continuously to Earth, and is being received by the 34-meter S-band antennas. And from time to time, when it's needed, they also use the 70 meters antenna. What happens now is that the power is slowly decreasing, so they are turning off all the instruments, and they estimate that if nothing else was wrong, by 10 years from now, in 2025, they will have to turn off all the instruments. This is how the spacecraft looks like, without thermal protections, but this is the way it looks. Here you have the main antenna. It's the 3.7 meter antenna. It has a subreflector, and what it does is the X-band is fed from here, is reflected and down to Earth. At S-band, it goes through this dichroic reflector to the main dish, and then is sent to Earth. So this is just known as the high gain antenna. Then there is a platform that contains all the cameras, spectrophotometers, and all kind of, let's say, sensors that really can detect light and send images. Here we have the propellants and the electronics. This is the power supply, is a nuclear reactor that goes there. Here we have folded and has to be expanded the magnetometer. And for orientation, the probe had two devices. One was a solar tracker that through a hole on the reflector would be pointing to the sun. And there was another tracker there that was locked to Alpha Carina star, just to have always the antenna pointing correctly to the Earth and the imaging system pointing to space, to the places they wanted to have. You have many, many images on the NASA website. The instruments on board could be classified in different ways, but this is the basic way to do it. In blue, you have those experiments that are still working today at the end of 2014. They had cameras and interferometers, spectrometers, radiometers, and photopolarimeters on board the platform, the scan platform. They also were getting information on cosmic ray and low energy particles and studying the plasma. And they could also measure, they keep measuring plasma waves and magnetic fields in the interplanetary space. And they will also carry some other experiments on radio astronomy, on planet radio astronomy and planetary, and also they took profit of the probes to test different communication schemes and protocols. Those probes are stabilized in 3 axes with a high resolution, 0.04 degrees. And for this they use 2 attitude controls. One is a sun detector for pitch and yaw control. By the way, if you have a plane or you have a spacecraft, and this is the tail and this is the nose, pitch is this, okay? And yaw is this motion, okay? So to correct for those 2, it's just one angle they needed, they use the sun detector because the antenna had to be pointing to the Earth and the sun was nearby always. The other, for roll orientation, roll is this motion, okay? And for this, they use a star tracker that locked to the Canopus, the Alpha Carina star, which is the second brightest star in the sky. Sirius is the first one, and then we have Alpha Carina. And they locked to both so they could stabilize, and through some gyroscopic monitoring, they could really keep pointing the platform. To maintain the trajectory and the attitude, they had some engines, small thrusters, 16, and they really were burning hydrazine, which is just the typical fuel for space. The mass was about 800 kilograms at launch, and only 13% was for the telecom payload. Today, the mass of the probes is about 100 kilograms less because they have already spent that amount of fuel. But still, they have 25 kilograms of fuel remaining there to go for at least a few years more. And the same thing happens with the power supply. They could not use solar cells at that distance from the sun, so they had to carry their own nuclear reactor in, and that's the only way to do it. In this case, it's a 7 kilowatt thermal output with the 3 units. And by thermocouples, they directly convert it to 450 watts. Since there is a decay, by now they are at about 2/3 of the rated power. And of that power, only 180 watts was allotted for the telecom system, but since the probe could not deal with thermal excess of power in some parts of them, they could only use at any time 110 watts of power in the transmitters. So this is just the limit, the power limit for the transmitters. This is the DC, the feeding power for the transmitters, and they could not go beyond this. It was launched in 1977, so if you look to the computers, you will see that there's nothing that could be compared with what we are familiar with now. The clock is of the order of megahertz and kilohertz, the CPU clock. And they process a number of instructions which are really quite low. But don't be surprised, those were state of the art at the time. They decided to put them on the probes. And it has 3 pairs of computers on top of it. The total amount of memory was 68 kilobytes. And for recording, they use a tape recorder with 8 tracks, and they could record in each track 12 images. And the total storage capacity was about 60 megabytes. So this is really a state of the art at that time in the early 70s. So this is about 40 years old, before the PC era and most of the things we are familiar now. The cameras were fairly good at the time. We had 2 cameras, one a wide angle, 200 millimeter focal length, and a 3.5 stop lens. The f3, this is just the ratio of the diameter of the lens and the focal length. And it has also a narrow angle, that's a tele, of about 1500 millimeter. Oh, I'm sorry, 1.5 meter. And the sensor was an analog Vidicom, 25 millimeters, and could store a picture for over 100 seconds. Now, they put a filter wheel on the face of this just to scan different colors, different wavelengths, and the image they were collecting was composed of 800 lines with 800 pictures elements, and for readout, they require 48 seconds. And they encode each pixel with 8 bits for the intensity, with the filter, the colors, and the intensity with this. So if you multiply the number of lines by the picture elements by the 8 bits, and you divide it by 48, this gives you a data rate for those images of about 100 kilobits per second. The problem is with Neptune, it's 6 times farther away from the Sun than Jupiter, and 30 times farther than the Earth. That means that if for a picture in Jupiter you needed 1 second, in Neptune you will need 36. On the contrary, on the Earth, 1/25 of a second. And also, the probe at the time was moving at the speed of about 20 kilometers per second. So stabilizing and getting a neat image, a sharp image, was not an easy task for them.